Hello and good evening, and welcome to today's NPTEL live interaction session. As you might be knowing, we are in the NPTEL course, Advanced in Post Concrete Design, and presently we are in week 11 of the NPTEL course. And as we have been doing always for all these weeks, we are going to solve some sample problems from week 11 of this course. And with that small introduction, I'm going to turn off my video and we will start today's session. Again, I would like to welcome you all to this live interaction session of the NPTEL course Advanced in Post Concrete Design. And this course is brought to you by NPTEL. And the course instructor is Professor Surya Prakash from IIT Hyderabad. And presently, we are in week 11 of this course. And this session is presented by me. My name is S. Lalit Sagar. I'm a doctoral candidate and PMRA fellow in the Department of Civil and Environmental Engineering at IIT Delhi. So this will be the agenda for today's session. And in today's week, we are dealing with Module 9, which is concerned with the aspects of serviceability, bond, and anchorage. So this module is divided into three parts. So in module 9.1, we considered the certain aspects of serviceability, especially the deflection, and specifically we differentiated what is uh, a short-term deflection and a long-term deflection, and then what are the influencing factors which are responsible for the deflection of reinforced concrete members, and then we calculated the short-term and long-term deflections of reinforced concrete beams as per the IS codal provisions. And in module 9.2, we considered um, the aspect of cracking in reinforced concrete members. So we studied the different types of cracks in RC members, and then what are the different factors that influence the crack width. And we also calculated the crack width as per the IS code provisions. And finally, in module 9.3, we considered the design of reinforced concrete members for the bond. So we know, as we saw in this week's lecture, that the reinforcing steel bars need to be embedded in the concrete members so that they develop the required, the bond strength, so that it doesn't get pulled off when they're subjected to the loading. So, in this particular part of the module 9, we considered the fundamental aspects of the bond strength, the basic mechanics of the resistance, uh, the bond resistance of the rebar, and then the different types of bond failure. Um, and then how do we calculate the development length as per the race code? And we also looked into the bar splices, that is the lap splice provided between the rebars when there is insufficient length of the reinforcing. So, with that introduction, we have around 15 questions today uh, to be solved. So, uh, we'll start with the multiple choice questions straight away. Okay. So, the question one is a theoretical one. So, which of the following parameters are evaluated under the limit state of serviceability? So there are six options, and we need to select all the correct answers. So as we know that, you know, basically as per the limit state design, there are two parts. That is limit state of uh, the limit state of strength and the serviceability. So we need to identify which of them come under the limit state of serviceability. So the remaining aspects will be dealt under the limit state of strength. Okay, so I'm going to pause for a few seconds. Then we can look at the correct options. Okay, so the correct answer for this particular question, the correct options for this particular question are options A, D, E, and F. Okay, so let us look at the explanation now. So there are two parts of the limit state design. So, so one is the limit state of collapse or the strength aspect, and the limit state of serviceability, which usually is considered to assess the performance of the building once it is constructed. Okay, so under the limit state of collapse or the strength, we design for strength, overturning, sliding, and buckling. Okay, whereas for the state of serviceability, we consider the deflection, cracking, durability, and vibration. Okay, so uh, as per this slide, which is taken from the lecture, we can clearly see that the parameters which fall under the limit state of serviceability are A, deflection, D, vibration, E, crack width, and F, durability. Whereas the options B and C, that is the bond strength and sliding, they are considered in the limit state of collapse. Okay. Okay. Let us move on to the question number two. So, in question two, what should be the minimum effective depth to be provided for a continuous beam of span 13 meters in order to satisfy the vertical deflection limits as per clause 23.2 of IS 456/2000. Okay, so whenever we are considering the design of a reinforced concrete beam, so first we need to start off with the effective the depth that needs to be provided. So as per clause 23.2, there is a certain uh, ratio that needs to be maintained when it comes to there's a certain number which needs to be maintained when we are considering the ratio of the beam span to the deflection. Okay, so we'll take that as the starting point, and then we are going to decide the dimensions of the beam and design the reinforcements and so on. Okay, so let us write down the data, and then we can proceed. See, so here let me take the pen. Okay, so what we have here is a continuous beam, right? And it is having a span of 13 meters. Okay, so now let us see what should be the minimum effective depth to be provided as per clause 23.2 of IS 456/2000. Okay, so this gives us the the basic value of the span to effective depth ratio for spans up to 10 meters. Okay, and here we have a continuous beam. So the continuous beam, the value of span to the depth, let me write the span as L and depth is the small d, that is 26. Okay, but we have this clause, that is 23.21 subclause B. So spans above 10 meters, the values in A can be multiplied by this particular number, that is 10 divided by span. Okay, so this uh, turns out to be, so 23.21. Okay, so as per uh, yeah, as per the B, this value turns out to be 26 multiplied by 10 divided by the span. Okay, so this ratio turns out to be 20. Okay, so now what do? We need to determine the effective depth now. So we know that the span is 13 meters. So L by D is equal to 20. Okay, so we will solve for D now. So D is given by L by 20, that is 13 into 10 to the power 3 divided by 20. So that turns out to be 650 mm. Okay, so it is clear that in order to satisfy this clause 23.21, that is to limit the deflection of the continuous beam, okay, which is having a span of 13 meter, we need to provide an effective depth of 650 mm. Okay, so as per this, option D is the correct response, just having a value of 650 millimeter. Okay, so we'll proceed to the next question. Okay, so in today's class, so what we're going to do is, first we're going to solve questions on this deflection. Okay, so we are going to solve the same, solve with the same order as we have considered in module 9.1, 9.2, and 9.3. So first we are going to solve the problem on deflection. Then we are going to consider the problem on crack width. Okay, crack width. And after that, we are going to be solving the problem on the bond. Okay, the bond length or the development of the arcimeters. Moving on, a simply supported reinforced concrete beam, which is having cross-sectional dimensions of 300 by 500 mm and having a span is 5 meter and carries a service load of 30 kilonewton per meter, which is the UDL. It is made of M20 concrete and it is reinforced with 4 Fe415 rebars of 20 mm diameter at an effective cover of 50 millimeter on the tension side. Okay, so we need to calculate the depth of the neutral axis in order to determine the short-term deflection. Okay, so this is we are going to solve this problem in order to determine the uh, short-term deflection of the reinforced concrete beam. Okay, so first we are going to start with sketching the cross section, and then we'll try to locate the depth of the neutral axis, and let us not forget that we need to solve this problem as per the working stress method. Okay, so let us sketch the cross section first, right? So we are having this bar of 300 mm width and 500 mm depth. Okay, and we are going to come back to this drawing of the cross section in order to solve the other problems. Okay, so we have four rebars, right? And let us provide, two hanger bars in the compression region, which is, not really necessary in our calculations, but we're going to still provide them, for the sake of completeness. Okay, and here the width is 300 millimeter, right? And the overall depth is 500. Overall depth is 500. And it is given that the effective depth is 450. That is the distance from the extreme compression fiber to the centroidal axis of the rebar. Okay, and this tension steel is 4 rebars of 20 mm diameter. Okay, 4 of 25, right? So we need to calculate the depth of the neutral axis now. Okay, so let us draw a sketch over here. Let us consider x as the depth of the neutral axis. Okay, and here let us consider m multiplied by AST. Okay, so this will be the region in tension, right? And this would be the region under compression. Okay, I'm just going to hatch it, right? Having a depth of B. So first, what is the equation in order to locate the neutral axis? We have bx square by 2 is equal to m into AST into d minus x. Okay, so first let us find out, the values that we need to uh, determine in order to solve this problem. So first we need to find out the modular ratio. So m is nothing but the modulus of elasticity of steel to the modulus of elasticity of concrete. So that is 2 into 10 to the power 5 divided by 5000 square root of FCK, that is 20, because let's remember that it is M20 concrete, right? So what is the value of M that we get? That is equal to 8.94. 8.94. Okay, further we need to find out the value of AST. AST is pi by 4 of 20 square, sorry, multiplied by 4, that is 1256.64 mm square. 1256.64 mm square. Okay, so we can start plugging these values in this particular equation, right? So from here, so we have 300 into x square by 2 is equal to 8.94 into 1256.64 into d minus x, 450 minus x. Okay, so when we solve this quadratic equation, right, we get the value of x as 149.92 mm, right? 149.92 mm. Okay, so I request all the participants who are watching this to confirm this. Okay, so we get the value of the depth of neutral axis as 149.9 mm, that is option C. Okay, so in this problem, to calculate the short-term deflection, right? So this is for a short-term deflection. we have the first step that we have done is we have calculated the depth of the neutral axis as per the working stress method. Okay, so let us proceed to the next part of this big question. Okay, so for the beam given in question 3, calculate the effective moment of inertia as per annexure C of IS 456 and compare it with the moment of inertia of the crack section. Okay, so let us start in this new slide, and we need to determine the crack moment of inertia, that is ICR, and the effective moment of inertia that is given as per the ISQ, right? So, okay, I think the equation, I mean, that particular clause is missing, but let us start uh, with determining the crack moment of inertia first, right? So this ICR value is given by bx cube by 3 plus m into ASD into d minus x squared. So this is determined by the parallel axis theorem, which you might be familiar with the concepts of in the concepts of engineering mechanics, right? So we have, let me write down the values over here. What the different values are. I'll take a different color for better contrast. So B is equal to 300 mm, right? And X is 149.92 millimeter, and M is 8.94, and ASD is 1256.64 mm square. Okay, and we know that the value of B is 450 mm. So when we plug all these values in this particular equation, right, we get the value of ICR as, okay, I'm skipping the substitution part, which you can just substitute and see. That turns out to be 1348.6, 1348.6 into 10 to the power 6 millimeter power 4. Okay, so the units are length raised to the power 4 for the moment of inertia. So that turns out to be, yeah, so there is option A and B, which both have the value of crack moment of inertia that is similar to what we got, 13.49 into 10 to the power 8. So now let us determine the value of the effective moment of inertia as per the annexure C. Okay, so yeah, let me draw a dashed line and we can start in the new column. So we have uh, this effective moment of inertia, that is I effective is equal to IR divided by 1.2 minus MR divided by M into Z divided by D into 1 minus X by D multiplied by BW by B. Okay, so now let us look at what each of these terms mean, right? So IR is nothing but the moment of inertia of the cracked section. So IR would be the same, that is 1348.6 into 10 to the power 6, right? Mm power 4, and MR, I suggest you to look at the IS code, okay? That is given by FCR into IGR, that is the gross moment of inertia, divided by YT. Okay, so what does each of these mean? So FCR is the modulus of rupture, that is 0.7 root of FCK, right? And FCK is 20 MPa. So as per that, we get the value of FCR as right in this line, which implies FCR is 3.13 MPa, and then the gross moment of inertia IGR is equal to BD cube by 12. So for the capital D, we need to consider the overall depth of the beam cross section. So that is 3125 into 10 to the power 6 power 4. Okay. Then YT is half of the total depth. Okay. So YT is equal to capital D by 2, that is 250 millimeter. Right? So once we substitute all these values, we get the value of MR as 39.125 kilonewton meter. Okay, so we get the value of MR, and M is the moment to which the beam is subjected to. Okay, so we can just draw the sketch of the beam over here. Okay, so it is subjected to a service load of 30 kilonewton per meter. Sorry for the sketch. And it is having the span of 5 meter, right? We have a span of 5 meters, and then what will be the bending moment at the midspan? That is WL square by 8. Okay, so that is 30 into 5 square divided by 8. So that turns out to be 93.75 kilonewton meter. 93.75 kilonewton meter. Okay, so that is the moment. Okay, so we have, let me write down the value of M over here because we took that from the previous slide. So M is equal to 93.75, right? Yeah, 93.75 kilonewton meter. So what are the values we need? We need to determine the Z. So Z is the length of the lever arm. So Z is equal to B minus X by 3. Okay, that is the uh, distance between the center of the reinforcing steel and the center of gravity of the concrete uh, compression block. Okay, so that gives me a value of, so we know that X is 149 millimeter, right? So the value of Z turns out to be, okay, it is close to 400 millimeter. Okay, so if there is any doubt in the calculation, you can always put it in the comment of the YouTube video. I'll be happy to uh, address them. Okay, so we got the value of IR, right? I'll take a different color. So we got the value of IR, we got the value of MR, and then M, and then we know the value of Z, D, X, and D. And here the BW refers to the width of the web, and B is the width of the beam cross section. So both are one and the same. So this term becomes 1. So once we substitute all the values, okay, in this equation, so once we substitute all these values in this equation, we obtain the I effective as, what is the value of I effective? I effective turns out to be 1415.6. Okay, 1415.6 multiplied by 10 to the power 6 millimeter power 4. Okay, so as per the IS code, it is mentioned that this I effective needs to be greater than the ICR or the IR. Okay, so let us go back to the options and see which one matches our results. So I effective is 14.15 and this is 13.49. So okay, so 14.16 and 13.49. So this is the value of effective moment of inertia, and this is the value of the correct moment of inertia, ICR or IR. Therefore, option E is the correct response. Okay. So first we determine the depth of the neutral axis, right? And then we determine the correct moment of inertia. Then we determine the effective moment of inertia. Now let us proceed in this question of the short-term deflection, right? So for the beam given in question 3, determine the short-term deflection at the midspan of the beam using the expression based on elastic theory. Okay, so when you consider the mechanics, right? Let me draw a simply supported beam subjected to a UDL, right? So this is having a span of how much? 5 meters, and it is subjected to a UDL of 30 kilonewton per meter, right? 30 kN per meter. So what will be the deflection at this midspan? So that we can call it as delta max, right? This is delta max. So delta max, or here it is delta S. So let us better denote by delta S, which was also the notation used in the class, that is given by 5 by 384 into WL to the power 4 divided by EI. Okay, so this EI is I effective. Okay, as per the mechanics, for a simply supported beam that is subjected to a UDL, this is the expression in order to determine the uh, maximum deflection. Okay, so let me write down what are the values for the various terms in this equation, right? So values are, right, so W is 30 kN per meter, okay, and L is 5 meters, and I effective is 14.16. 14.6 into 10 to the power 8 millimeter power 4. And what is the value of EC? That is the elastic modulus of concrete. EC is 5000 root FCK. That turns out to be 22,360.7 MPa. So let us plug all the values in this equation, right? So delta S is equal to 5 by 384 into 30 into 5000 raised to the power 4. Let us remember that we need to express all the values in terms of Newton and millimeter. Okay, so this 30 kilonewton meter becomes 30 Newton per millimeter. Okay, because uh, there is no conversion between kN per meter and Newton per millimeter. Okay, and then this length is expressed in terms of millimeter, and E is 22360.7, MPa is Newton per millimeter square, 22360.7, and I effective is 14.16 into 10 to the power 8. So the value of delta S that we get is 7.7 millimeter. So from that we can say that option A is the correct response. Okay, so uh, from this we have determined the value of the short-term deflection that turns out to be 7.7 millimeter. Option A is the correct response. Okay, so the next question is for the beam given in question 3, determine the deflection due to shrinkage as per Annexure C of IS 456-2000. Okay, so here we have this is the expression for the deflection for shrinkage. So we know that a reinforced concrete member can undergo shrinkage over time due to the loss of moisture, okay, and other environmental parameters. So this ACS, or let me call it as delta CS, okay, delta CS is given by K3 into psi CS into L square. Okay. So here we know that we are considering this simply supported beam. So the value of K3 is equal to 0.125, right? And we know the value of L, which we can substitute it later. Let us find out the value of psi CS. Okay, this psi CS is equal to, this is called as the shrinkage curvature, that is equal to K4 multiplied by epsilon CS divided by T. So what is the value of K4? So K4, it depends on the value of this, uh, the reinforcement of uh, the percentage steel in tension and compression. So for the moment, let us ignore the value of PC and let us find out the value of PP, that is the percentage of steel in the tension zone. So that is given by AST, right? AST divided by BD into 100. Okay. So B into small d, that is the effective depth into 100. Right. So let us substitute that value, that is 1256.64 divided by 300 multiplied by 450 into 100. So that gives me a value of how much? 0.93. Okay. So PT is 0.93, right? So for the time being, we can ignore the value of PC. We can take it as 0. Okay. So uh, since it is the value of PT minus PC is in this range, we can use this formula to calculate the value of K4. Okay. So let me calculate the value of K4 over here, right? I'll take a different color for better contrast. Okay, so we have the value of K4 is equal to 0.72 multiplied by PT minus PC by square root of PT. So that can be simply written as square root of PT, right? Because PC is 0 and PT upon square root of pt is square root of pt. So 0.72 multiplied by 0.93. Okay, so the value of K4 is how much? 0.694. And then what is the value of epsilon Cs? Right. Epsilon Cs, we can look up the clause 6.2.4. 6.24 of IS 456 2000, that is the same code. And here the value of epsilon Cs is here given as 0.0003. Okay, 0.0003 or 3 into 10 to the power minus 4. Okay, this is the value of epsilon Cs, right? So, yeah, I think we can, go ahead and find out the value of delta Cs directly, right? So, delta Cs is given by K3, that is 0.125 into psi Cs, that is given by K4, that is 0.694 into epsilon Cs is 0.0003 divided by the overall depth, that is 500, multiplied by L square, that is 5,000 square, right? 5,000 square. Okay, so once we solve that, we get the value of delta Cs as 1.30 millimeter. Okay, so this is the final answer. So option A is the correct response. Okay, so now we have determined the deflection due to shrinkage. Okay, so let me remind you that this is part of the long-term deflection. Okay, so the shrinkage effects and the creep effects, they start to kick in after a few months or few years after the construction has been completed, where you can see the effects predominantly of these factors, right? So the deflection of the beam due to shrinkage is 1.3 millimeter. Okay, let us proceed to the next question now. So for the beam given in question 3, determine the deflection due to creep as per Annexure C of IS 456 2000 and assume the age of concrete as 28 days while loading and 70% of the moment is due to the permanent load. Okay, so creep, we have this in Annexure C of IS 456, we have the following clause in order to calculate the uh, deflection of creep, right? So in order to obtain the deflection due to creep, that is ACC, due to the permanent load, we need to first determine the AICC or delta ICC, that is the deflection due to initial plus the creep deflection due to the permanent loads obtained using an elastic analysis with effective modulus of elasticity, that is ECE. Okay, and then this AI or the delta I permanent, that is the short-term deflection due to permanent load using the EC. Okay, so for this term, we're going to consider the effects of creep, but for this term, the effects of creep, that is incorporated through the elastic modulus. So the effect of creep is not considered. So let us first, try to find out the elastic modulus by considering the creep effect, right? So here we have value of EC, or rather ECE is equal to EC over 1 plus theta. Okay, so theta is the creep coefficient. So this is equal to 1.8, I believe. Oh, it is 1.6. Okay, so theta is equal to 1.6 for 28 days. Okay, so I would suggest all of you to look at the clause. Okay, in the IS code, I have not um, taken note of the exact clause where this is um, where we get this value of theta, but we'll take this and we'll find out the value of epsilon CE. I'm sorry, ECE. That is, ECE is 22360.7 divided by 1 plus 1.6. This gives me a value of 8600 8600.3 MPa. Okay, so we need to use this value while we are determining the deflection due to creep. Okay, so this will be the value of ECE, and the value of EC, again, to reiterate, that is 22360.7 MP. So we can see that upon the action of sustained loads, okay, the value of the elastic modulus or the stiffness reduces by almost one third. Okay, it reduces by almost 1/3 of this particular value, which we're going to see in the deflection calculations later on. So we need to consider the cross section now, and we need to determine the location of the neutral axis for this value of ECE. Okay, so let me proceed with the location of neutral axis. So the equation is b x square by 2 is equal to m AST into d minus x. Okay, so what is the value of m? M is equal to ES divided by EC, that is 2 into 10 to the power 5 divided by 8600.3, which gives me a value of how much? 23.255. Okay, 23.255. So as the value of this EC reduces, the modular ratio increases. That will come into play when we are determining the location of the neutral axis. Okay, so let me write down the values. We have b is equal to 300 mm, right? Uh, yeah, better I'll write down the equation, then we can actually uh, solve for the value of x, right? So 300 into x square by 2 is equal to 23.255 multiplied by 1256.64 into 450 minus x. So this is a quadratic equation in x. So when we solve this equation, we get the value of x as how much? So the value of x is 214.3 millimeter. This is the value of x that we're going to get. Okay, we'll proceed to the next part. So once you have calculated the neutral axis, we need to determine the crack moment of inertia and the effective moment of inertia, right? So let me take a different color. Right. Yeah. So ICR B x cube by 3 plus M AST into D minus x square, right? Okay, so let me solve by substituting these values, right? 300 into what is the value of x? 214.3, right? Yeah, 214.3 cube divided by 3 plus what is the modular ratio? Modular ratio is 23.255, right? 23.255 multiplied by AST 1256.64 into D minus x whole square, that is 450 minus 214.3 whole square, which gives me the value of the crack modulus as 2607.64. 2607.64 into 10 to the power 6 millimeter power 4. Okay, so this is the value of the crack moment of inertia. Now we need to find out the value of the effective moment of inertia, right? So we have the value of effective moment of inertia, or I effective, that is equal to ICR or IR, okay, depending on the notation, divided by 1.2 minus M R, okay, divided by M. Okay, so this is the crack moment, right? Multiplied by Z by D into 1 minus x by D multiplied by BW by B, that I'm going to neglect over here because that is equal to 1. So what else do we need in this particular equation? That I'm going to write down in this particular space. Okay, I'll take a different color also so that we can differentiate, right? So we have MR is equal to uh, okay, that is FCR, right? FCR into IGR, FCR into IGR divided by YT. Do we have another blank slide? Oh, yes, we do, but I'll try to fit in over here only. So the value of FCR is 0.7 root FCK, that is 3.13 MPa, and IGR is same, that is, I reckon it is 3125 multiplied by 10 to the power 6 millimeter power 4, and YT is 250 millimeter, right? So once we solve this, we get the value of MR is equal to how much? 39.125. 39.125 kilonewton meter, and we need to find out the value of M. Okay, that will be 0.7 into 30, that is the permanent load, that is taken as 70%. Okay, 70% of the moment is due to permanent load. Okay, 0.7 into 30 into L square, that is 5 square, divided by 8, and the value of M turns out to be 65.625. 65.625 kilonewton meter. So we have the value of MR, then we have the value of M, and we need to find out the value of Z. Let me write down the next slide, right? Z is equal to D minus X by 3, that is 450 minus, I think 214.3 by 3. 214.3 divided by 3. So that is how much? 378.57. 378.57 mm. We have the value of Z also now figured out. Yeah, I think that's it. We can start plugging all the values and obtain the correct answer, right? So ICR is okay 2607 into 10 to the power 6 divided by 1.2 minus MR is 39.125, right? 39.125 divided by 65.63 into Z is 378.57. Okay, 378.57 divided by D is 450 multiplied by 1 minus 214.3 divided by 450. So I effective is equal to, I need to manage that in this space, that is 27.82 multiplied by 10 to the power 8 millimeter power 4. Okay, so this is the correct answer, 27.82 into 10 to the power 8. Okay, so now we need to find out the value of the deflection due to creep, right? So deflection due to creep, that is, I'll take a different color and solve it. Hmm. Now delta Cp, delta I plus Cp minus delta I, okay, that is given by, so let us first calculate the value of delta I plus Cp, that is the deflection due to the initial plus creep due to the permanent load obtained using the uh, effective modulus of elasticity, right? So that is 5 by 384 W L to the power 4 divided by E, e CE into I effective. Okay, let me write down that. And here let me write down the value of delta I also. So that is given by 5 by 384 multiplied by W L to the power 4 divided by EC into I effective. So the only difference between these two is that here we are considering the modulus of elasticity due to creep, and here we are not considering the creep effect on the modulus of elasticity. And mind you, we need to consider the 70% of the total load as the permanent load, right? So let me plug in all the values now, right? 5 by 384 into W is how much? 21, right? Into 5000 over 4, and EC is 8600.2 into I effective is 27.8, 27.28 into 10 to the power 8. So that gives me a value of 7.14 millimeter. 7.14 millimeter. And then here this is 5 by 384 into 21 into 5000 power 4 divided by, here EC is 22,360.7 into the effective modulus is same 27.28, effective moment of inertia, I'm sorry, so that will be 2.75 millimeter. So you can see that increase when we increase the moment of inertia, sorry, the elastic modulus, okay, the value of deflection reduces. Okay, so delta Cp is equal to 7.14 minus 2.75, which gives us a value of 4.39 millimeter, right? So option B is the correct response. Okay, so now we have calculated all the terms corresponding to the short term and the long term deflection. So now we need to see if the beam satisfies clause 23.2a and clause 23.2b. Okay, so what is the relation of the deflection with respect to these two clauses? Do they satisfy or not? Okay, let's see that. Okay, so we are going to consider the final deflection over here. Okay, as per clause 23.2, right? 23.2a. So here delta is equal to, right, delta S plus delta shrinkage, that is SH, plus delta creep. Okay. So we know that the value of delta S is how much? So delta S was 7.7 millimeter and the shrinkage was 1.3 and the creep was 4.4. Okay, that is 7.7 plus the shrinkage is 1.3 and the creep is 4.4. So the delta total is 13.4 millimeter. Okay, so this let us check. So this, I would say, this is the effect due to the the permanent load. Okay, on the other hand, the subclause B is with respect to the erection of partition and the application of finishes. Okay, so here the difference between these two delta is that the delta S is replaced by delta I. Okay, we're going to see that in the next part of this question. Now let us check with the permissible value. Okay, so here we can write it as delta permissible PR is equal to L by 250, that is 5000 divided by 250, which gives me a value of 20 millimeter. So it is less than the permissible deflection. So clause 23.2a is satisfied. Okay. Now let us check for clause 23.2b, right? Clause 23.2b. Okay. So here this delta is equal to delta initial, that is the initial loading or the imposed loading, plus delta SH plus delta CP. Delta CP. So that we can express that as, what is delta I? Delta I we can consider from this particular equation, right? We're considering 70% of the load. Okay, that is 7.14. Okay, So here we have 7.14 plus shrinkage is 1.3 and the creep is 4.4. So that gives a value of how much? 12.83 millimeter. That is 12.83 millimeter. So as per this clause, subclause, what is the permissible deflection? Delta permissible is equal to delta by 350, right? That is 5000 divided by 350. So that gives me a value of 14.3 millimeter. Okay, so the beam satisfies this clause 23.2b as well because it is less than the permissible deflection of 14.3 millimeter. So if we are not able to satisfy the deflection criteria, we need to go back and we need to redesign the beam by providing a higher depth and greater reinforcing steel in the tension region. Okay, so we can say that the statement A is the correct option. The beam satisfies clause 23.2a as well as clause 23.2b with respect to the deflection check. Right. So we'll proceed to the next question, and we're going to take up the problem on this crack width. Okay. Give me a few seconds. Yeah. So let me read out the question first. It is required to determine the crack width in the beam at points A, B, and C. So these are the points. A is at the corner, and then we have B, which is right vertically below this first rebar, and then C, which is at a depth of 2, 2 by 3 into d minus x from the neutral axis. Okay, over here. we need to determine the crack width at these points. Okay, so consider that the beam is simply supported and over a span of 6 meters. It carries a UDL of 15 kN per meter. Calculate the depth of the neutral axis and crack moment of inertia. Consider that these rebars are of 20 mm diameter and the concrete used is M25, and take the effective cover as 50 mm. Okay. So the first thing for us is to determine the depth of the neutral axis and the crack moment of inertia. Okay, let us proceed to do that now. Okay, so it is having the same dimensions as we considered for the uh, deflection problem, but the only difference is that the area of steel provided is different. Hmm. So let us see that. So first we need to find out let me write down the equation first. That makes the thing simpler, right? So for the location of neutral axis, location of neutral axis. Hmm. Okay, so the equation is bx square by 2 is equal to m into ast into d minus x. So we are finding it as per the working stress method, right? So the value of b is 300 mm, right? And the value of x is to be determined, and ast is pi by 4 of 20 square multiplied by 3. That is how much? Mm, that is 942.5 millimeter. 942 942.5 millimeter. That is the value of AST. And then we have the value of D. Okay, D is 450 mm. D is 450 millimeter, right? And we can start solving the problem. But before that, we need to find out the value of M, right? So we have value of M is equal to ES by EC. That is the ratio of the modulus of elasticity of steel to the concrete. So ES is pretty much the same for different types of steel. 2 into 10 to the power 5 divided by 5000 square root of 25. That is 25,000. So the value of M turns out to be 8. Okay, so we can, yeah, let me write down it here. 300 into x square by 2 is equal to 8 into 942.5 multiplied by d minus x multiplied by d minus x, that is 450 minus x. So we get the value of x as how much? 127.35 millimeter. Okay, this will be useful for us in the further calculations. Okay, so we have located the neutral axis, right? So let us proceed to find out the crack moment of inertia, right? I'll take a different color now. Okay, ICR or IR is equal to bx cube by 3 plus MAST into d minus x square. So we can start plugging those values. 300 into 127.35 cube divided by 3 plus 8 into 942.5 into 450 minus 127.35 square, which gives me a value of how much? 991.47. 991.47 into 10 to the power 6 mm power 4. This is the value of the correct moment of inertia. So option D here is the correct response. Okay. For the given cross section, the depth of the neutral axis is 127.35 mm, and the correct moment of inertia is 991.5 into 10 to the power 6 millimeter power 4. Okay, we'll proceed to the next part of the question. Next question. For the beam given in question 9, determine the mean strain at the level considered, that is epsilon m, for points A, B, and C. Okay, so how do we determine the value of epsilon m? So epsilon m is epsilon 1 minus B into h minus x into A minus x divided by 3 times ES AS into D minus x. So what is epsilon 1? Epsilon 1 is the strain at the level considered. Okay. So first we need to find out that value of epsilon 1. Okay. So how do we do that? So in order to determine the epsilon 1, first we need to obtain the stress at the level of the reinforcement. And from that, depending on the strain profile, we can determine the value of epsilon 1. Okay, so let us, yeah, how do we make it simpler for you guys? Okay, let me start off with a sketch over here. That might make it easier for you. We'll draw the sketch over here. So it's having a width of 300 millimeter and depth of 500, right? The width is 300, right? And the overall depth is 500. Okay, and let me mark the value of this, the value of x as well. So what is the value of x? That is 127.35, right? 127.35. Okay, and what is the value of this remaining part? That is 450 minus. Okay, let me take the calculator, find out the value. 450 minus 127.35, that is 322.65, right? Okay, then we have this, which is at a depth of 2 by 3 into d minus x. Okay, I'll take this red color to represent that values, to represent those points. Okay, this is point C, this is point A, this at the corner, and here smack at the bottom of this we have the point B. So what is the distance between the neutral axis and the point C, the vertical direction? So that is 2 by 3 into this value, that is 215.11, that is 215, 1 millimeter. Okay, so now first what we need to do is we need to calculate the value of the moment. Okay, and then the stress and then the strain. Okay, we need to draw the strain distribution as well. I'll prepare for that, over here. So this is the neutral axis, and this the strain distribution would be looking somewhat like this. The strain is 0 at the location of the neutral axis, right? Okay, so we need to determine the value of the moment. So it is having a span of 6 meters, UDL of 15 kilometers per meter. Okay, let me solve it over here, right? This is the UDL, right? and the span is how much? 6 meters, right? 6 meters. So the value of m is w l square by 8. So that is how much? 15 into 6 square divided by 8. So this is the service load. So the value of m is 67.5 kilonewton meter. Okay, so this is the value of m. So from the value of m, how do we determine the stress at a particular point? That is stress at the level of steel, that is given by m by I is equal to F by Y, right? F by Y. So we need to determine the stress at the level of steel, that is FCS, that is stress in concrete at the level of steel, that is this one. Okay, let me write it as epsilon CS, right? I'll write it as epsilon CS. Okay, so the stress in concrete at the level of steel, that is given by M by I, M by ICR, that is the crack moment of inertia, multiplied by what is Y from the neutral axis, that is D minus X. Okay, D minus X. Okay, so that is given by FCS is given by what is the value of M? 67.5. Yes, 67.5 kilonewton meter, right? Divided by what is ICR? ICR is 991.5, right? Okay, excuse me. Yeah, 991.5 into D minus X, that is 450 minus what is the value of X? 127.35. Okay, which gives me the value of FCS as, that is the stress in concrete at the level of steel, that is equal to 21.97 MPa. Okay, how do we find out the value of epsilon CS now? Epsilon CS is equal to FCS divided by EC. Okay, that is 21.97 divided by 25,000. That gives me a value of 8.79 into 10 to the power minus 4. That is the value of epsilon CS. Okay, now we need to find out the value of epsilon 1. So epsilon 1 is the strain at the level considered, calculated, ignoring the stiffening of concrete in the tension zone. Okay, so we need to find out epsilon 1. Okay, epsilon 1 at this level and epsilon 1 at this level. Okay, so let me make use of the space over here maybe. Okay, epsilon 1, I'm going to solve it here. Mhm. Epsilon 1 at A or B, right? That is given by, right, epsilon Cs into capital D minus X divided by small d minus X. Okay, so that gives me a value of how much? 1.015 into 10 to the power minus 3. 1.015 into 10 to the power minus 3. That is the value of epsilon Cs. Okay, so moving on, we need to find out the value of epsilon 1. Epsilon m at A or B. Okay, so wait, I might have to copy this and put it in another slide. Okay, let me keep the annotations. Okay, I'm going to copy this, copy and paste it. Yeah, I think we can go now. We are good to, yeah. So let me, okay, so I will select all this and delete the annotation. Okay, so the purpose here is for me to show you how the epsilon m is coming about. Okay, so here epsilon m is equal to epsilon 1 minus b into h minus x into a minus x divided by 3 into es into as into d minus x. Okay, so we have epsilon 1. We are doing the calculation for epsilon 1 at A or B because both the points A and B, they're in the same horizontal plane, right? So we have epsilon 1 is 1 into 1.015 into 10 to the power minus 3. 1.1.015 into 10 to the power minus 3. Okay, and what is the value of B? B is the width of the section, that is 300 mm. And what is the value of H? H, I reckon that is the overall depth of the section, right? Let me confirm. Yeah, that is the overall depth, that is 500 millimeter, right? And X here is 127.35. Yeah, 127.35. Okay. And then what is the value of A? A is the distance from the compression phase to the point at which the crack width is being calculated. That is from here to the points A and B. That is the overall, the full depth. And this value is different when we consider the point C. Okay, so A is equal to 500 millimeter, and we know that ES is 2 into 10 to the power 5 MPa, and AS is how much? 942.5. 942.5 mm squared. And ultimately B is 450 mm. Okay. So when we plug all these values, the value of epsilon 1 at A and B, so that turns out to be 7.867 into 10 to the power minus 4. Okay, this is the value for, uh, sorry, here. This is the value of epsilon 1 for points A and B. Okay, so now, uh, oh, sorry, this is the value of epsilon m. Okay, so we got this value. Now let us find out the value of epsilon m for the point C. Okay, so in order to find the value of epsilon 1 for point C, okay, so basically it is nothing but, yeah, let me do the calculation here. take a different color now. Okay, epsilon 1 for point C is equal to 2 by 3 into epsilon CS. Okay, because this point C, it is at a distance of 2 by 3 from the neutral axis, right? So this we can substitute. Here it is epsilon CS is 8.79. Okay, so the value of epsilon 1 is 5.857, right? 5.857 into 10 to the power minus 4. Okay, so when we consider the point C and use the same equation. Okay, so the only difference I believe in, the few differences are epsilon 1 is different. It is 5.857 into 10 to the power minus 4. B is same. Okay, and H is same. The X value is also same. A is, we need to calculate the distance from the top to here, that is 215.1 and 127.35. Okay, I will calculate that value for you. Okay, 127.35 plus 215.1. Okay, so that is the value of A. A is, okay, the value of A is 342.45 mm. Okay, and ES is same, AS is same, and the effective depth is same. So when we substitute all these values, in this equation, we get the value of epsilon m for point C as how much? 4.54, 4.54 into 10 to the power minus 4. Okay, so actually, for points A and B, the value of epsilon m is 7.9 into 10 to the power minus 4, and point C, the value of epsilon m is 4.5 into 10 to the power minus 4. Okay, this is for points A and B. Therefore, option C is the correct response. So we'll move forward. We have another 5 questions, for today's session, right? After this, for the beam given in question 9, determine the crack width at points A, B, and C as per annexure F of IS 456-2000. Okay, so we have this, so let me write down the value of epsilon m first, for the different values, right? So I think it is better to, sort of make, a table over here, right? So let me write down the value here. Okay, so we have point A, okay, point B, and point C, right? And I'm going to write down, the different variables so that we can calculate the different values over here, right? I think that will be an effective way of representing all the data, right? So, yeah. So here I'm going to write down the parameters, right? In order to calculate the crack width, right? So we have, let me write down epsilon m, right? The mean strain value that we have calculated earlier. Then we have ACR, okay, and then we have the crack width itself. Okay, and I'm going to write down the values which are common for all of them. So C min is the minimum cover, that is 40 millimeter. Okay, and H is equal to how much the overall depth of the section, that is 500 millimeter, and the value of x is 127.35 millimeter. Now why Cmin is 40 millimeter? Because if we consider this section, right, so the effective depth is 50 mm, right? So you subtract this 10 millimeter, and you know this 50 minus 10, that is the minimum uh, cover, or the clear cover, that is 40 millimeter. Okay, and now what is the value of this ACR, right? ACR is the distance from the point considered to the surface of the nearest longitudinal bar. Okay, so we know that for point B it is 40 millimeter. Okay, let me take a different color so we can have better contrast, right? So this ACR will be in millimeter, and this WCR also will be in millimeter, right? Those are the units, and epsilon m. Okay, for points A and B, 7.9 into 10 to the power minus 4, or 7.87, right? 7.87 into 10 to the power minus 4 mm per mm. Those are the units of the strain. Okay, then for point C, what is the epsilon m? That was 4.54, right? 4.54. Yeah, 4.54. So ACR, we need to calculate the values now. Okay, now let me draw a simple diagram, right? We have three bars. So we need to calculate the distance from this point to the point of uh, you know, the nearest surface of the longitudinal reinforcement. Okay, and let us consider that this is the point C. Sorry about that. Okay, I'm going to draw this. I'm going to write down this, mark it using this color, right? So this will be, so the value of A until the surface of the longitudinal rebar. Okay, B, and here let us call it as point C, right? So from geometry, or from the Pythagoras theorem, we can find out the distance between the point considered to the surface of the nearest longitudinal bar. Okay, and B is quite straightforward. It is just 40 millimeter, and the value of ACR for point A. So for point A, the value of ACR is 60.71 millimeter. Okay, 60.71 millimeter. And what about point C? For point C, the value of ACR is 108.6 millimeter. 108.6 millimeter. So when we substitute all these values in this particular equation, we obtain the surface crack width at points A, B, and C. That turns out to be, I'll take a different color once again. Let me take green now. So for point A, the value of WCR is 0.144. Again, the value is in millimeter, and for point B, the value of WCR, that is 0.105, and for point C, the value is 0.108. So we can round it off as 0.14, 0.11 and 0.11. 141111. So option A seems to be the correct response. Okay, so option A is the correct answer. So we have done one problem on deflection and one problem on crack width. Now let us solve the problem for the bond or the development length. Okay, so we are given a cantilever beam, right? For the cantilever beam shown below, that is subjected to a total factored load of 100 kilonewton. Determine the development length required, okay, for the tension and compression steel, right? So here this is the tension steel because it's a cantilever. The top fibers are subjected to tension. The bottom fibers are subjected to the compression. So let us proceed to find out the development length. So in tension side we have 25 bars and in the compression side we have 16 bars. So as per the IS 456, let us calculate for tension first. So to determine the development length in tension is more critical, I would say, because the rebar can undergo failure or the pullout or the rupture um, or the fracture under the tensile load. So phi is 25 right? So LD is equal to 25 into what is the sigma CS. So we are going to consider the 87% of the yield load. Okay, that is we are considering that the full potential of the rebar in tension is being reached divided by 4 times tau BD. So which concrete is it? It is M20, right? So it is 1.2. Are there any modification factor? Yes, because when we are considering this deform bar, we need to increase by 60%. Okay, so that will be into 1.6. So the value of development length in tension, that is 117 sorry 1175.3 millimeter. Now we'll do the same exercise for the bar and rebars and compression. Okay, so for compression 16 bar, phi is equal to 16 millimeter, right? So the value of LD here is given by 16 into 0.87 into 415. I hope I have specified the value of Fy in the question. Yeah, it is given and it's deformed bar. So 4 into the tau BD is same, depends on the value of M20 or the grade of concrete 1.2. Now there are two modification factors, that is increase it by 60% for the deformed configuration and increase it by another 25% because the bar is in compression, right? I think it's simple, straightforward. So the value of LD that we get in compression, that is 601.75. So let us calculate the value of LD that is actually being provided now. Okay, so the answer is 1175 and 602. 1175 and 602. So option A is the correct response. The second part of the question is if the provided lengths are adequate. Okay, so what is the length that is being provided? LD in tension, LD provided is equal to 280. Okay, plus we are having this hook. So this hook is 8 times the diameter, right? 8 times the diameter. So when we are having a 90-degree hook, we are considering 8 times the diameter plus another 300 mm which is being embedded inside the column. So that turns out to be 780 millimeter. So 780 millimeter is definitely less than the value of 1175. So we need to increase the development length in tension. So what is the status in compression? In compression, the development length provided is 300 millimeter, but the actual required is 600 millimeter. So we need to increase the development length. We can, sort of provide a 90-degree hook and we can embed it in this direction. So in order to fulfill this, what we can do is we can actually extend it and we can actually embed it in this direction. Okay. And for the tension steel, we can actually embed it further into the depth of the column, into the, the lower height of the column. So let us look into the next part of the question. I mean, the next question. Okay. It is all part of a big composite problem. So for the cantilever being given in question 12, determine the anchorage length, okay, based on the area of the required steel. So it so happens that we perform the analysis and we obtain the design moment. Okay. And then depending on the design moment, we provide the, we calculate the area of steel required. Okay, but this always turns out to be, like for example 3.5 bars or 3.8 bars, so which we round off and provide it to, let's say, 4 bars, and that would be the AST provided. Okay, so considering these two, parameters, that is AST required and the AST provided, we need to determine the anchorage length. Okay, now let us proceed to determine the anchorage length required based on the area of steel that is required for the beam. Okay, so we'll perform a simple analysis over here. So we have a UDL of 50 kN per meter acting over a length of 2 meters. Okay, so here the value of M is WL square by 2, that is 50 into 2 square by 2, that is 100 kilonewton meter. So now we need to find out the value of mu limit to decide whether it can be designed as a singly reinforced or a doubly reinforced section. So that is given by uh, yeah 0.36 into XU max by D 1 minus 0.42 XU max by D into BD square into FCK, right? So when we actually do the calculation by considering this B, let me write down the values just so that we are not lost over here, right? So we don't feel lost when we are doing the calculation, right? B is equal to 200 millimeter and D is equal to 400 minus 40, which is the effective cover, that is 360 millimeter. That is the value of D, and XU max by D. That is what? Because it is Fe415 still, that is 0.48, right? So mu lim here, that is the limiting moment of resistance, that is how much? 71.52 kilonewton meter. That is the mu lim. So we need to design it as a doubly reinforced cross section, doubly reinforced. So how do we do that? So we can actually, make use of the SP16 table. Okay. So SP16 1980 on page 109 of the PDF. Page 109 of the PDF. Okay, so when we open the page 109, actually it corresponds to page number 86 in the document. Okay, in page number 86. So what we can do is we can find out the value of this mu by bd square and then d dash by d. From that we can obtain the value of pt and pc. Okay, I'm going to write down those values, right? So we have mu by bd square, that is 100 into 10 to the power 6 divided by 200 by 360 square, which gives me a value of how much? 3 point, sorry, 3.858. 858. And then we have the value of d dash by d, that is how much? 40 divided by 360, that is 0.11. So basically we have the value for 0.10 and 0.15. So first we need to interpolate between these two values, 3.8 and 3.9, right? So interpolate between these two values and then interpolate between these two values, okay, between 0.10 and 0.15, and then we obtain for a value of d dash by d is equal to 0.11 by interpolating between these two columns. So from that we first obtain the value of PC and PT and PC. So from that we can obtain the value of AST and ASC. Okay, I'm going to write down those values directly that we can ascertain, that you can obtain later. If there is any doubt, we can always discuss later. So PT and PC, that turns out to be okay, let me write down in another color. So what do we have here? Like PT is equal to 1.2978 and PC is 0.3619. So correspondingly the value of AST would be 934.42 mm square and ASC would be 260.57 mm square. So how do we determine the the development length required? I'll make another, I'll take a different color once again. Okay, now LD required, right? LD required is equal to LD multiplied by AST, um, AST required by AST provided. So let me do it for tension first. So for tension, the value is 1175.3, right? Yeah, so it was 1175.3, 1175.3 into AST required, that is Uh, yeah, 934.42. 934.42. And what is AST provided? That is 2 bars of 25 mm diameter. That is pi by 4 into 25 square multiplied by 2. That is 981.75. 981.75. So which gives me a value of how much? Yeah, 1119, or you can round it off to 1120. So we can carry out the same exercise for LD required in compression. So LD required in compression, that will give me a value of how much? 390 millimeter. Okay, you may please verify that. 390 millimeters. So LD required in tension and compression are 1120 and 390. So option D is the correct response. Okay, so let us quickly proceed to the last two questions for the day, right? So we have here the tension and compression zones are reinforced with 20 millimeter and 12 millimeter. Okay, so instead of 25 dia, it becomes 20 dia. Okay, and instead of 16 millimeter dia, it becomes how much? 12 millimeter. Okay, so what we will do is, we are going to consider the same equations over here. Okay, that is uh, 5 into sigma s by 4 bd, right? So I'm going to do for tension, then we can figure out for the compression yourself. You can take it as a homework, right? So here LD is equal to, LD is how much? 5 sigma s by 4 tau bd. 5 sigma s by 4 into tau bd, that is 20 multiplied by 0.87 into 415 divided by 4 into 1.2 into 1.6, that is for tension. So LD turns out to be how much? Uh, yeah, 940 millimeter. 940.23 millimeter. So similarly, in compression, I'll write it in a different color. So that turns out to be LD in compression. That turns out to be how much? Uh, 451 millimeter. 451.3 millimeter. So looking at this, mind you, this is for 12 millimeter diameter. So the correct option is option B. That is 940 and 452. Okay, so when we reduce the diameter, it reduces the requirement of the development length as well. Okay, you can just compare this value 940 and 452 with this value 1175 and 602. Okay, it is slightly lesser when compared to you know when compared when when we use a higher dia of the longitudinal rebar, we need to provide a higher development length as well. Okay, so as we can see, in question 14, option B is the correct response. So we'll move on to the last question of the day. So which of the following steps can be taken if the development length provided for the reinforcing steel is inadequate? So out of the 5 options, we need to consider we need to pick the correct answer. So increasing the dia of longitudinal steel, that is not effective, because if we increase the dia, we need to provide a higher development length. So we can provide hooks of 90 degree or 180 degree, so that will increase the development length required. We can decrease the grade of steel provided we are providing the proper strength and anchorage length in the design. So this is a viable option. Okay, because when you when you decrease the grade of steel, the required development length also decreases. We can increase the grade of concrete, that will increase the value of the bond stress, that is tau. That is also a viable option. And finally, we can decrease the die of longitudinal steel, because when you decrease the diameter, then the development length also decreases, as we have seen in the question 15. So options B, C, and D are viable options to uh, you know um, decrease the required development length of the reinforcing part. Okay. So with that, we have come to the conclusion of today's session. So here is a quick recap. So we did a problem on the serviceability, um, especially for the deflection. Then we considered one problem on the serviceability, that is cracking. Then ultimately we performed the design for the bond or the development length. So I thank you all for your attention, and we'll meet again in the next week.